In this video lesson, we're going to be looking at Chapter 3, Section 1. The topic is quadratic functions, so we want to remind ourselves about a little bit of background for quadratic functions. Quadratic functions are polynomials. In a previous lesson, we saw that a polynomial can be a single term or the sum of two or more terms that contain variables with whole number exponents and real number coefficients. So we can't have any like fractions that don't result in whole numbers. We can't have any exponents that are negative numbers. And our coefficients have to be real numbers. They can't be imaginary. So just a quick reminder about terms. Terms are what we add or subtract, and they can be composed of many factors. So here we have some examples of polynomial functions. So f of x, some equation, is defined to be x cubed minus 6x. So we have two terms here. X cubed is a term and 6x is a term. In 6x, we have the factors 6 and x. Factors are what you multiply. And in x cubed, we can think of that as having a factor of x that occurs 3 times being multiplied. These are examples because this exponent 3 is a whole number, and the coefficients of each of these two terms are real numbers. This coefficient is 1, and this coefficient is 6. And I mean, a quick identifier is that we don't see any i's. All right, so g of x is another equation that is also a polynomial. We have an exponent that's a whole number, and we don't have any i's involved here. And then we also have a couple more examples of polynomials here. Now, in this section, in Chapter 3, Section 1, we're going to be studying quadratic functions. So the only quadratic function that we have, that polynomial, is this one right here, because the highest exponent is 2. All right, some non-examples of polynomials would be these 4 right here. The reason this function fails to be a polynomial is because that exponent is not a whole number. In g of x, this exponent is a whole number. However, we see that in this term right here that we have an imaginary number. In this example, this is not a polynomial because this exponent, real quickly, we can identify and see that that's not a whole number. And in this example right here, g, the pi is okay. Pi is a real number. But in this term right here, because we have 3 terms here, in this term right here, we can see that we have an imaginary coefficient. So that's why those fail to be examples of polynomial functions. A quick reminder too that quadratic functions are second degree polynomials. That means the highest exponent is 2. So second degree, highest exponent is 2, and may or may not have other terms. So it could be that we have f of x equals x squared, and that still is a quadratic function, even though we're not adding or subtracting other terms. As a matter of fact, we've seen this right here in section 2.5. We've seen that the graph of this quadratic function right here is what we call a parabola. It has what we call a vertex at the origin. The origin is the ordered pair 0, 0. And this graph would open upward, kind of like in this bowl-shaped figure right here. All right, and then in real-world quadratic functions, they can be used to model paths of projectiles. And projectiles are just objects in many sports that are thrown, kicked, or hit. And the paths of these projectiles are modeled by quadratic functions. All right, and the graph of any quadratic function is a parabola, as mentioned up here. And the most basic parabola is the common or parent function f of x equals x squared, which we looked at right here. All right, before we actually get into our objective in this section, which is to graph quadratic functions, let's look at some continued background about quadratic functions that'll help us in this section. Okay, it's probably going to be there's going to be some situations where when we're looking at quadratic functions and we're looking for what we call zeros, that we might end up with some imaginary answers. So let's remind ourselves where the imaginary numbers come from. They come from square roots that have negative radicands. And radicands are just what falls underneath the radical. So these are all negative numbers that fall underneath the radical. These are negative radicands, and they result in imaginary numbers. We've done a little bit of work with this, and so we want to remind ourselves about that background to help us here in a minute when we put all this together. All right, the imaginary unit I, lowercase I, is defined to be the square root of -1. And we also know that if we were to square both sides of this equation, I squared is equal to -1. So this is probably a good thing to memorize right here, is that I squared is equal to -1. All right, let's remind ourselves about some imaginary numbers. Now, this is not just simply square root of 25, positive 25, which would result in 5. Okay, a while back, a few weeks ago, we saw that we could actually take the -25 and rewrite it as -1 times 25. And when we multiply underneath a radical, we can separate, not when we add. If this was plus or minus, we couldn't do what we're about to do here. We could break this apart and say that this statement is equivalent to the square root of -1 times the square root of 25. I'm going to work down here. I'm going to work down because I'm running out of room here. So the square root of -1 is defined to be I, so I replace this notation with I, and I kind of look in here and go, can I simplify this? Yes, I can. The square root of 25 results in 5, and it's common practice. Now I'm going to work across again. It's common practice to put the I behind the 5. So the square root of -25 is equivalent to 5I. Okay, in the second example right here, again, we could separate and make it -1 times +7. So I'd have square root of -1, which results in I. Now I have square root of 7. Well, the square root of 7 does not simplify, and so we're going to leave our answer just like this. We're going to leave the square root after the I. If we were to write it square root of 7 times I, it might get confusing with someone looking at this thinking that I belongs underneath the square root, but it doesn't. So kind of to avoid that kind of mistake, we usually put the I in front of radicals. If we don't have a radical like 5, then we usually put the I behind that number. All right, the square root of -20. Well, think about this being -1 times 20. So the square root of -1, out would come an I. So the I comes out from this negative, and we're left to multiply by the square root of 20. Well, the square root of 20 can be broken down or simplified because we know that 2 times 10 or 4 times 5 equals 20. And in those pairs of factors like 2 and 10 or 4 and 5, I kind of inspect these numbers and go, you know what? The square root of 4 is actually 2, so I can simplify. This might be the better choice of factors that multiply and give me 20. So I'm going to rewrite this as the square root of 4 times 5. And remember, 4 and 5 are both underneath the radical. All right, again, I can break this apart, and I can make this the square root of 4 times the square root of 5. The square root of 4 is actually just 2, and this is all being multiplied. So I can take this 2 and put it in front of the I and make this 2I square root of 5. So all these are being multiplied together. These are all factors of the answer. Yeah, over here we have a few more examples. Remember, this can be square root of -1 times the square root of 9. This gets replaced with I. The square root of 9 is 3. The order we would put it in would be 3I. Square root of -18. Okay, you don't have to break it apart like this. You can just take out the square root of -1 and immediately make it I. But that leaves 18 under the radical. Think of the factors of 18. 1 and 18, 3 and 6. Oh, I think I missed 2 and 9, didn't I? I like to go in order. So, and then 2 and 9, and 3 and 6. And I kind of look at these numbers, these factors, and I go, well, I know 9, if I were to square root 9, that would be 3. So I'm going to rewrite 18 as 2 times 9. So remember, this is I times square root of 2 times square root of 9. Square root of 9 simplifies to 3. How do I take and manage all this? Well, I'll take the 3, put it in front of the I, and then multiply it by the square root of 2. It wouldn't be wrong and correct to have this in a different order, but it's just that this is kind of common practice, the way in which we order these factors. Okay, this right here, I know I'm going to have I. Square root of 11 will not simplify, so I'm just done with this right here. All right, some more background that we need before we actually get into our main objective of graphing quadratic functions. Some more background is that we need to consider, okay, what are real zeros versus imaginary zeros? So real zeros versus imaginary zeros. All right, the language here is find the real zeros. They're also known as x-intercepts, where we cross the x-axis. You might hear the word roots or solutions, and all these are synonymous. If you're asked to find x-intercepts, it's the same thing as being asked to find roots, solutions, or zeros in any kind of, arrangement of that. All right, so how do I find the real zeros versus imaginary zeros of this quadratic function? Well, over here, let's just remind ourselves that if we're finding an x-intercept, we think about the x-axis, the real number line. That's what that's called, the real number line. Not imaginary number line, but real number line. Okay, all these x values on this x-axis are real numbers. If we're going to find an x-intercept, that means that we're looking at a point that falls along the x-axis. Well, every point that falls along the x-axis has something in common. And what those ordered pairs have in common is that the y-coordinate is always 0. So if you're asked to find the real zeros, another way to think of that is, oh, I've got to let y be equal to 0 and solve that equation then. So find the real zeros for this function right here. Before I do go through that, I want to go ahead and remind ourselves about when we graphed this back in 2.5. We saw that the common function was x squared, but we see that we have a minus 4, not with the x, but outside the x. There's no parentheses here. So this actually indicates that this quadratic function would have a translation of movement down 4. So think about where the parent function is, the common function. The vertex, or that turning point, is at the origin. But instead, for this equation, I would move down, shift down that vertex. Okay, I would shift it down 4 places to 0, -4, and my parabola would open like this. Okay, so does this equation or quadratic function have any real zeros or x-intercepts? It does. Right here and right here. And we're supposed to find the x-coordinates of these x-intercepts. Remember, the y's are 0. So our objective to find the real zeros is to let y be 0 here. F of x is equal to y. So I'm going to let f of x be 0, or y be 0, and set that equal to the function x squared minus 4. All right, now how do I solve this? Now we have to kind of dial that in our brain. Now how do I solve this? Well, I do know that this is a difference of 2 squares. It will factor into x minus 2, x plus 2. But I also, instead of using factoring, can use the strategy of the square root property. Meaning, let's isolate the x squared and bring in the square root. So I'm going to add 4, and I'm going to get x squared equals 4. Now I'm going to trade sides. I like to have x squared on the left. Okay, to solve this, now I'm going to bring in that even root to both sides of the equation. Because an even root will undo an even power, if they match, I have to bring out x, but because it's even, I need to put absolute value around x. Now let's look over here. Square root of 4 is 2. That's nice. It's simplified. If it didn't, I wouldn't, I'd just bring this down. To remove the absolute value, I would have to make an adjustment to plus minus over here. So I actually have 2 x values that make this equation equal to 0. So, and let's kind of think about what we have over here on the graph to make sense of these answers. Okay, if I wanted to, I could write them out as x equals -2, comma, x equals 2. And another way to think about this, if you were asked for the x-intercepts, you would have to report your answer as ordered pairs to identify those locations on this graph. So it looks like that makes sense that these x values would be -2 and 2. So These are our solutions here, if you will. These are our solutions. These are our x-intercepts. And so any of these are the correct answer, whether you just put x equals -2, 2, or if you put the ordered pairs. And it really just depends upon how they're asking the question. Because the question was asked as find the real zeros, this would probably be the way that you'd want to report your answer. If you were asked to find the x-intercepts, then usually we give that answer as an ordered pair. All right, a reminder before we go to these other three quadratic functions here is that this is a parabola. It opens upward like a cup. Okay, we found the real zeros of -2 and +2. We call this turning point the vertex. This is the bottom of this graph that opens upward. This is the vertex. And as a matter of fact, this is the lowest, this is the location of the lowest y value, the lowest y that's on this graph. This is called an absolute minimum. This parabola will not go any further down than y equals -4. So that language, vertex, absolute maximum, is going to come up in the section in a minute, but we've already had the opportunity to talk about it. So when we see it again, you'll have that familiarity with that language. All right, let's come over here and look at this function. Before I actually find the zeros by replacing f of x with 0 and solving, I want to get a graph of what this looks like based on 2.5's work that we did. All right, if I'm going to graph x squared plus 4, I know the parent function starts at the origin, meaning the vertex is there. The graph opens upward. But this plus 4 from section 2.5 tells us that we need to shift the graph not left or right, but up 4. So if I put a tick mark here of 4, then what I'm doing is I'm translating the parabola, the parent function, up 4 units. Okay, let's use this graph to help us understand what answer we're about to get from the real zeros. Well, I can clearly see from this graph right here that it never crosses the real number line. So I have no x-intercepts. If I have no x-intercepts, then I'm not going to have any roots or solutions. I'm not going to have any real zeros. I'm going to actually end up with some imaginary zeros. All right, so I shouldn't get a real answer here when I go through the process of finding real zeros. So remember, that language means replace y, which is f of x, with 0. Think of the similarity with this equation right here. Okay, now I want to solve this. Can I factor this? This does not factor because this is not a difference of 2 squares. So if I can't factor it, then let me go ahead and use the square root property. So I'm going to subtract the 4. Bring down x squared is equal to -4. I'm going to trade sides. Okay, we're going to use the square root property, which means next bring in the square root. But look what happens when you put the square root over that negative number. We know from our work up here that we're going to get an imaginary answer. Again, let's just continue through the process so that our work supports that we have no real zeros. So square rooting a square brings out the x, but with absolute value. Okay, I can bring out the square root of -1 as an I, and square root of 4 would give me 2. So the arrangement of that would be 2i. Remove the absolute value, and you're going to get the -2i and the +2i. So let's go back to the question. It says find the real zeros. Well, I can clearly see that I don't have any real zeros, so we need to respond to that question. So we just would say no real zeros. And when someone's inspecting our work, they can see the mathematical process that we went through to get these imaginary zeros, so we can respond and say no real zeros, which on the graph, it means this graph will not cut through or touch at any point any x value on the real number line. All right, for these two right here, I don't know what the graph looks like because I don't see that I can use my transformational graphing background from section 2.5. These equations, quadratic functions right here, are not in what we call standard form. We can't identify the changes up, down, left, or right because we don't have that parenthesis with a square on it from our previous work. So for these two right here, I can just share with you what the graph looks like based on my using a calculator to put this in, a graphing calculator to put this in and get a graph. This is what the graph looks like of this quadratic equation. It actually has a y-intercept. So this is the x-axis and the y-axis. Okay, this graph actually has a y-intercept at 3. So this ordered pair right here, where this graph of this parabola, it's going to cut through the y-axis at 0, 3. And to get the y-intercept, we know that any point that falls along the y-axis is going to have an x-coordinate of 0, but then we'll have a y-coordinate that may be 0, but probably is something else. Just think about real quick by inspection, if you were to plug in 0 for all the x's in this equation, that would go to 0, that term would go to 0, and I'd be left with 3. So this constant, what we call this c value, this constant right here is actually our y-intercept. So over here, just kind of look at that idea. Okay, I know this is a parabola. It's going to open upward. We'll see in a minute that's because a, the coefficient on the x squared term, is a positive number. This graph's going to open up. What do I know about this graph? Well, it's not in the format from the previous section to know how to kind of transform it left, right, up, or down. But what I do know is if I let x be 0 here and here, that the result would give me 5. So this parabola is going to have a y-intercept of 0, 5. Okay, and that's about all I know right now. Here in a little bit in this section, we're going to learn how to take these quadratic functions in this form, and we're actually going to learn how to graph these as well, compared to what we did in the past when we learned how to graph them when these quadratic functions were written in a different form. Anyway, let me come over here and just kind of finish showing you what this graph looks like. Okay, and in a later video, we're going to learn how to get this graph right here without using a graphing calculator. But anyway, this is what this graph looks like. Now over here, I went ahead and graphed this previous, and this is what this graph of this parabola looks like. All right, so let's make a prediction. Does this quadratic function have any real zeros? Well, I see one's going to be here and one's going to be here. So I will have 2 real zeros as a result of my algebraic work here. Well, over here, does this parabola ever cross through or touch the x-axis? No. So when I do all this algebraic work right here for this quadratic function, I'm not going to get any real answers. They're going to be imaginary, like I got right up here. All right, so let's go back here to this function. Now our objective, again, find the real zeros. Okay, what does that mean? That means y equals 0. All right, so how do I solve this quadratic equation? Well, the different strategies we learned were factoring, square root property, and quadratic formula. Well, let's see if we can factor this. We need factors. We need the factor sum chart. We need factors of a times c, or 3, that sum to b, that sum to -5. Well, the only factors of 3 are 1 and 3, but there's no way when I make one of these, or both of these negative to get +3, and I add these, there's no way I'm going to get -5. So what that tells me is that I cannot factor this quadratic equation. Remember, I cannot use the square root property either, because the square root property, I have this term right here with an x in it to the first power. So the quadratic formula is what we need to use to find the answers, or the zeros, or the x-intercepts, or the roots, or solutions. So quadratic formula will work for any quadratic equation to solve it. So I'm going to go ahead and put the quadratic formula right here in front of me again. I'm going to go back up to my quadratic equation, and I'm going to identify that a is 1, b is -5, and c is 3. So just working downward, nice, neat, and organized, x equals, I'll start with the easy part first, the denominator. 2 times 1 is just 2. In the numerator, I want the opposite of whatever b is. B is already -5, so I'll make that positive. b is -5. I will use parentheses with the square, minus 4 times a, which is 1, and times c, which is 3. So I'm going to have 5 plus or minus, and then the 2's here. So now let's look underneath the radical. I would go right to my calculator, and I would get 25 minus 12, which is 13. Now on your calculator, make sure and do parentheses with the -5, square it, and then minus 4. I would not use parentheses here. It just gets too crowded. I would do minus 4 with the multiplication dot times 1 times 3. All right, and as I look at this square root, I want to ask myself, can I simplify that? No, I can't. There's not a perfect square to pull out. So my answer is actually going to be 5 minus the square root of 13 all over 2. And my other real zero is x equals, with another fraction bar, the 5 plus the square root of 13 over 2. And you could change these to decimals if you wanted to. If you wanted to go to your calculator and change these to decimals. And when you do change these to decimals, you should get 2 positive answers. And that would those each would represent both of these x-intercepts right here. So whatever value this is, probably is going to be this left x-intercept, because this is the smaller value because I'm subtracting. And then whatever value this is on the calculator, whatever decimal number that is, 2 or 3 or whatever, that would represent that x-intercept or that real zero. So these are our real zeros. All right, so for this one right here, we know we're not going to have any real zeros. Our answers should be imaginary. So let's find any real zeros. Let y be 0. We're not going to be able to factor this one. We are going to have to go to the quadratic formula. Let's identify as a comma. A is 1, B is 3, and C is 5. So opposite 3 plus or minus. Parentheses are not necessary around that positive number. 3 squared minus 4 times A times C. All over 2 times A in the formula, so that's just 2. Okay, writing the -3 down, the 2 down, don't forget the plus minus here. 9 minus 20, that's going to be -11. Okay, let's kind of take a look at what we have here. That's a negative underneath the radical, so we know that's going to be an I. So let's pull out the I from the negative under the radical, and then the square root of 11 remains because we can't not simplify that. So we can see from here that I have no real zeros. And if you wanted just to go down and say, okay, no real zeros because I see the I, that's fine. But just as a reminder, I could separate these imaginaries into 2 imaginary answers. So -3 minus I squared of 11 all over 2. And the other non-real zero is x equals -3 plus I squared of 11 over 2. Okay, but I still want to respond and say no real zeros. Which again means I have no x-intercepts. Okay, and visually we can see that we don't have any x-intercepts. This is actually the graph of that quadratic function, which it is. So in the lesson that we're actually going to be doing, we're going to be taking different quadratic functions like this, and based on a set of steps, we're going to be drawing those parabolas that are represented by those quadratic functions. So we'll do that in the next video lesson.